Hello, John. Are you online? Can you hear us?
Yes, I'm here.
Ah, great, great, fantastic. Speaking from high altitude, very nice. So it's very kind of you to spend your time with us, right? Getting out of your splendid location and doing some research talk while being on vacation. So we can only appreciate this. So very kind of you. And so John, I mean, he's a distinguished scientist at Google Research, and he's leading the applied research organization at Google. And in particular, he looks at climate change, but he has a huge background. It's not only climate change. I think this is really cool because I think we cannot, pursue these important issues like sustainability and fighting climate change if you don't have a kind of holistic view, because there's so much, much hinges on taking, manufacturers into account, reaching from legal sides of things, and taking the society along, and who knows what. So I think it's so great that John has all these backgrounds. So he looks into AI, and he looks also into graphics and planetary science. I think probably he's the only one amongst us who had looked into planetary science. Analog circuits, quantum computing. I mean, it's really impressive. Numeric analysis, computer vision, human-computer interfacing, support vector machines, computational geometry. And for his works in computer graphics, he received the Technical Academic Award in 2006. So he's a very distinguished speaker, and I'm very, proud and flattered that we have him here amongst ourselves. And yeah, so I think, John, the stage is yours. So please go ahead and enlighten us.
Oh, well, thank you so much for inviting me. I'm very happy to be here and sort of share lessons that I've learned about climate change from Google. So I'll give a very broad talk about how artificial intelligence or machine learning can fight climate change. And the structure of my talk is, first I'll give a brief introduction to the sort of problem of climate change, which is both a societal problem and a geophysics problem. Then I'll sort of go from the small to the large, where first we'll talk about, does using AI in general make the problem of climate change worse? And we'll talk about carbon-aware computing, which is a method to sort of minimize the effect of AI or other large-scale computations on the climate. I'll make a little side trip to talk about what you can do if you want to help. And then there's many possible applications of AI to climate change. So I'll talk about AI for world modeling, and then I'll try to sort of summarize, after I wander through these topics, all the lessons that I've learned so you can benefit from them. So first, let's talk about the climate. The global warming is caused by the greenhouse effect. And you might not realize it, but the amount of heat that's bouncing back and forth between the ground and the atmosphere is much larger than the average amount of solar radiation absorbed by the surface itself. So we're in a very nice greenhouse caused by the atmosphere, which is good because that keeps the Earth's surface at 14 Celsius. But it also means that if you even small changes in the greenhouse gases could cause large changes in the average temperature. And in fact, there's the model of the atmosphere is a very simple model, which is just a budget. So essentially, you put carbon dioxide into the atmosphere if you burn something, and and some of it gets absorbed by the oceans and the land, but the rest of it stays for centuries. So you can view the atmosphere as having a fixed carbon budget. And here we're showing on the y-axis the number of gigatons or billion metric tons since 2018 that we have, and essentially there's a function that maps the amount of CO2 that you put into the global mean temperature. And at some point, unless you have negative emissions technologies, there's just a point of no return. So if we just keep going on our path, we can't reach 1.5 Celsius if we go past 2031 on our current path. So we don't, and 2 Celsius is sort of at the edge of danger, and 1.5 is much more preferable. So we really have to take very rapid actions. It's a little bit even worse than that because you can't stop at a time. This graph shows what would happen if you instantly stopped all carbon dioxide emissions, but you can't actually do that. If, for example, in 2030 we stopped new fossil fuel infrastructure, letting the old stuff decay away, that's roughly equivalent to a 3.3% annual reduction. And even if we stopped in 2030, there would still be a lot of inertia in the system in terms of existing infrastructure. We'd still shoot past 2 Celsius. You'd have to actively decommission and rapidly decommission old fossil fuel infrastructure. And even then, you would get by a few tenths of a degree Celsius. So if you assume a 3.3% annual decrease, in other words, we don't do anything new bad, but we still have the old infrastructure, and you plot what the final temperature rise after 2100 is, you'll see that even today, or even last year, if we just stopped doing new infrastructure, we reach 2 Celsius, which again is at the considered the edge of the danger point. And every year that we delay is another, a fraction of a degree that makes things ever more dangerous because we don't know where the tipping points are. For example, at 3 Celsius, the Amazon might turn into savanna. So the problem is incredibly urgent. So to give you some structure about how you can fight climate change, there's 2 broad categories. There's climate mitigation. So that's doing things like reducing emissions, or absorbing carbon dioxide. And then there's a whole bunch of work in climate adaptation, it's already getting to be a problem. In fact, here I'm in California, and the Pacific Northwest in the United States is having record temperatures. My house is up to 45 Celsius, and it had never been even above 40 before. So, we have climate changes upon us, and we need to also adapt to it while we make sure that the damage doesn't go worse. So in this talk, I could talk about many different things in terms of mitigation and adaptation. But in this talk, I'm going to talk about the direct carbon footprint that Google and perhaps other companies have and how we're reducing that. And then for climate adaptation, I'm going to talk about how we can cope with the more severe weather that will be caused by increased carbon dioxide, which as the temperatures warm up, there's more on average, more moisture in the atmosphere. So that causes more severe weather. So let me go into this. So how does Google reduce its carbon footprint? Google itself uses a lot of electricity to run its business and run its data centers. And we actually purchase renewable energy to run our business. But it's a bit tricky because if you participate in a grid, there are no green electrons or coal black colored electrons. It's all just gets dumped into the same grid. So I'm going to explain sort of metrics that we use to figure out our carbon footprint. And as part of that, I want to just do step 1. So we're going to use artificial intelligence to help climate change, but I want to make sure that we're not actually adding to the problem. And let me go into this briefly. So artificial intelligence, the best place to run them is in data centers with advanced processors such as tensor processor units or TPUs. And these data centers use electricity. And do they produce carbon dioxide? Well, it depends on where the electricity comes from. So here's the first lesson that I've learned, which is that climate change boils down to accounting. My cynical definition of accounting is the quantified art of assigning costs or perhaps laying blame. As I mentioned, electricity is shared on the grid. We do buy renewable energy, but how do we know what our carbon footprint is if it's coming out of the shared resource? So let me show you a graph of how I think about this. Let's say that the demand is just a constant line, just for simplicity. That's that blue line at 1 unit. The problem with renewable energy is that the sun doesn't always shine and the wind doesn't always blow. So here's a typical week of renewable power. Sometimes when you purchase a certain amount of renewable power, you get more than you expect, where the orange curve is above the blue line. And sometimes you get less than you expect because it's perhaps night or maybe the wind isn't blowing. So you have a gap, and then you have to fill that gap, which is shown in green, by grid sources, which might be have fossil fuel. For example, there may be a coal plant running. So we used to, up until recently, have this renewable energy metric where we took the renewable energy, which is the area under the orange curve, and we divided it by the demand energy, which is the area under the blue curve. And it turns out that ever since 2017, Google, at least under this metric, was 100% renewable. So the average area of the orange curve, the renewable, is about the same as the average area of the blue curve. So essentially, that if you consider that to be net zero carbon, we don't actually contribute, but that's again averaged over the entire year in all locations. Now that doesn't reflect it's fine to use this metric when not very many people are using renewable energy, but as we get closer to 2030, everyone is going to have to start using renewable energy. We can't assume that the extra renewable energy that we've purchased will be absorbed by someone else, because they'll also be trying to purchase renewable energy. So we've come up with a new metric called carbon-free energy. And so what it does is it ignores any excess. We're assuming that the excess renewable power is going to get thrown away. And so it's this, we take the CO2, the negative, the bad metric, in other words, we want this to be driven to zero, is the CO2 that's used in these green regions, which is just whatever the CO2 intensity is times the amount of energy we use divided by our demand. So if we can't purchase, if there are hours that go by where there's a gap, we have to pay for that CO2 in effect under this metric. So our current goal as a company, Google wants to drive this metric to zero by 2030. So it's a very strict metric. And in fact, it implies that the grid itself that we participate in, and if we draw any energy from the grid, the grid itself has to be zero carbon. Now that we have this metric, this carbon-free energy metric, my second lesson is don't fear the burden, the CO2 burden from AI. So if you go, Dave Patterson had this paper this year, which measured how much it took to train a machine learning model using the CFE metric in Iowa, which is a very renewable heavy area because we have a lot of wind in the United States in the Midwest. And training a 130 million parameter model, this happens to be a language model, 100 times only takes about 2 metric tons of CO2. Now, a small climate project that you might work on might save 3,000 metric tons of CO2. And of course, some of our projects are much larger than that. So if we're applying AI to fight climate change, the benefits are much higher than the costs in terms of CO2, even using this stricter CFE metric. So I would encourage people not to worry about using machine learning to fight climate change, that the benefits should be much higher than the costs in terms of CO2. Let me tell you one way we're going to decrease this CFE metric, or the CO2 metric, which is by carbon-aware computing. And this is work by Anna Radovanovic, Ross Koenigstein, and a large team at Google. So what is carbon-aware computing? Well, it turns out we don't have to always run a computation exactly when and exactly where a user requests it. And so we can exploit flexibility to actually reduce the amount of carbon dioxide that we emit. Now, some jobs have flexibility when they can run. So there are large batch jobs like processing videos or training machine learning models or doing simulations, where we don't have to run them exactly at 3 o'clock, say. They could be delayed. So we can do this, you can view this graph, which is normally our load might be even, and that's sort of showing by this conventional compute load, but we can actually shift in time the jobs to when there's more solar power or more wind power. And therefore, we can actually reduce the amount of, by matching our computation to the renewable energy curve, we can actually reduce and improve our CFE metric. Now, some computing jobs have flexibilities about where they can run. The previous jobs that are batch tend to be very data heavy, and therefore you want to run them in the data centers where the data resides. Other jobs, for example, G Suite, or it doesn't have to be Google, user-facing applications like Office or Salesforce, they could run somewhere else because they tend to be very light. They don't tend to consume terabytes of data. And in fact, there are starting to be carbon-aware compute resources, such as there's a region picker in Google Cloud that shows you which regions are the most carbon efficient, and Microsoft also has a carbon-aware Kubernetes. And for those kind of jobs, you can imagine you have 3 data centers, and if you have one job that sort of pops up and it wants to run in data center 3, but data center 3 has a lot of carbon, you shift it to a different data center 1, which is now much more green and much more renewable. So by pushing things in space, you can actually get a lot of advantage. The vision is that we can use this flexibility to reduce overall CO2 emissions. We have to know, while we do this, we actually have to know in advance what the carbon intensity of the grid is going to be, so we can match our compute loads to the carbon intensity. And eventually this will get very widespread and reduce CO2 emissions overall. Now, just to briefly go into how this works, there's a conceptual division. Of course, every data center is very complicated. It has all this real-time scheduling. So what we do is we have do day-ahead plans where we have some planning that takes into account the carbon intensity of computing. And what it does is it essentially shifts the capacity in time or space to try to improve the carbon intensity of the computation. So this is what it looks like. Normally there would be some default cluster capacity that's in purple. What we do is we make a virtual capacity curve based on this carbon prediction, which is shown as these red dashes. And so we actually push delay insensitive jobs to, perhaps to the next day or to the evening or to another. And if it's space insensitive, it might push to another cluster. So so that's how it's worked. Essentially, it's an optimization problem which changes the virtual capacity curve. And the math is essentially convex optimization, and there's a trade-off parameter between the carbon footprint and the cost to the infrastructure, because by pushing jobs around, you're not using 100% utilization. So you can you have to spend a bit more on infrastructure and on peak power. So there's a trade-off that you can choose, and but it seems like it's a pretty soft trade-off. So the lesson is that load shifting works, and that just observably, the CFE score varies about 46% over the hours of day of a typical data center. It varies from 3 to 91% across data centers. So shifting in time and shifting in space actually works, and this is a form of demand response. You can try it too, even if you're a listener to this talk and you're not a computer scientist, you don't have a data center. All you need to do is shift your electricity use in time or space, but you need to have a prediction of grid carbon intensity, and we get that from our partners. One is called Tomorrow, and the other is called Watt Time. You can try this too with their APIs. Okay, so let me talk about the urge to help. Many engineers, this happens to me at Google, and even when I go outside to conferences, they want to work on climate change. They might not be experts at climate change, and they want to use their technical skills, not necessarily their economic or political power. And are there enough projects out there about climate change where engineers can volunteer to help? And the question is, how can we make this scale? How can we connect all these engineers who want to help with all the problems that there are in the world? And the fourth lesson I have is optimizing as part of your job. So let's just take the United States. The United States emits about 6 billion tons of CO2 equivalent greenhouse gases per year. The census says that there's about 2 million non-computer science or non-computing engineers. So if we chop up the responsibility, that means each engineer should try to solve about 3,000 tons per year of CO2 equivalent emissions. So what I tell people is stay in your job, use your expertise, and save a moderate amount of carbon. This is where the 3,000 tons comes from. So if you can stay in your job and figure out how to save 3,000 tons, engineers have a lot of leverage because they touch systems that tend to be automated or tend to be replicated. Okay, if you're interested in this, you can, a couple of different resources, workonclimate.org. There's a Slack channel and has access to experts, or climatechange.ai is a set of machine learning experts that make tutorials and conferences. Excuse me. Okay, so let me, in the last bit of my talk, let me talk about what machine learning is good at, or AI is good at, because then we can figure out how to use AI to fight climate change. Now, I can't talk about all the different possibilities. We have this climatechange.ai group. Forgive me. The climatechange.ai group is has made a very nice overview paper that's very long and detailed. It has 13 different sectors that you could look at. I highly recommend the paper. I was a co-author. But let's sort of go in this talk as kind of a broad overview. So there is this danger that AI is the favorite hammer that everyone likes, and the climate applications are nails, and it's not terribly clear that we're actually nailing something and fixing the climate, or just sort of hammering pieces of metal. So how do we know that the AI will help climate change? Well, from what I've seen, there are three matches between artificial intelligence, machine learning, and climate. And here are the three kind of matches. One kind is if there are autonomous climate-aware decisions that can be made. So decisions that might happen very rapidly that you don't want to ask a human to do. You can train a machine learning model to make decisions. The second one is large-scale sensing of the world. So there are satellites, there are aerial images, there are very large amounts of data that are being absorbed in real time. Machine learning can help absorb that data and make benefits to the climate. The third style is large-scale modeling of the world. So we can make very large models and scalar models using machine learning. The examples I'll give for each one of these, I won't go into it very much. For example, the autonomous climate-aware decisions, DeepMind used machine learning to control the cooling of the data centers, and that saves about 40% of the energy of the cooling, which is a fraction of the data center in total energy. And so that's an example of machine learning doing sort of continuous climate-aware decisions. My favorite example of large-scale sensing in the world, which is deployed already, is a thing called Project Sunroof, which is part of Google's Environmental Insights Explorer. What we did was we took aerial images of cities, isolated the houses, figured out which way the area of the roof of each panel of the roof and the direction of the roof, and then we estimated how much money would you save if you installed solar power PV on top of your roof. And you can go and type in your address if you're in certain cities and find out how much you save. So that's a kind of way of mapping sensing back into climate impact. And I'll spend the rest of this talk, while I'm running out of time, on doing large-scale modeling of the world. So this is going back to climate adaptation. There's going to be more floods in the future because of increased atmospheric moisture. And we model the world with machine learning in order to forecast this floods. And this is work done by Sela Nevo in our Israel lab. Right now, even today, even as climate change is starting to bite, flooding is a huge impact. Hundreds of millions of people are affected by floods, or even billions of people, and it actually causes a lot of damage. We have a flood forecasting product. What it does underneath the hood, it first has a hydrological model where it models where the water flows in a river basin. It actually then does a hydraulic model where it actually figures out where in the river channel the water should go. And then if we see that the water is going to start to intrude on inhabited areas, we actually have a warning distribution system where we alert people on their mobile phones, telling them that they might be in a potential flood zone. So I mentioned the hydrological model, which actually sort of models the mass of water, and it takes into account many different possibilities like precipitation, melting snow, water evaporating off of lakes. It also models underground flow, which is important for keeping track of the water balance. Now, the classic approach in doing hydrology is you build a model that's very much matches what the physics of the hydrology is. So you have an evaporation model, you have a storage model, you have a percolation model. It's conceptually very simple, but it's over parameterized. There are many, many, many parameters in each of these boxes, and so it tends to overfit in the words of machine learning, and it has to be manually calibrated. It's unclear whether the calibration is correct in all places. So what we do is instead we made a machine learning approach where we didn't actually plug any physics in. We just took rainwater, precipitation, and then estimated the discharge, and then trained it on a series of observations that we had in a river basin. And it uses something called an LSTM architecture for doing time series prediction of the discharge. And in fact, we have a nicer model, which is called HydroNets, which actually which includes a little bit of physics. It includes for example, it has if a river comes together in 3 branches, the state comes together from the 3 branches. And so this is like an LSTM whose communication looks just like the river basin and the convergence of the rivers. It turns out that down into the right here is better, and the hydrological model that's based on machine learning is actually a better model than the old physics model. And we find this again and again in climate-related modeling systems, where instead of trying to calibrate individual subpieces of these very, very complex models, it's better to do end-to-end calibration using machine learning. And just to close the loop, we have a system called Google Public Alerts. And so when the hydrological model and the hydraulic model together figure out that a region is going to be flooded, we alert people either if they're in search or if they're in maps, or they could be part of Android and have a smartphone notification. And we also help local authorities communicate emergency messages if outside these 3 channels. So the lesson I learned from a lot of this AI modeling of the world is you can replace empirical models with machine learning with just enough physics. And so instead of a very granular model, you can have just enough physics like, oh, there are 3 rivers that are coming together here at this point. And that's makes a better model of the world. And therefore, we can do better climate adaptation and perhaps better mitigation too. So in fact, a useful world model that I'm hoping that the community will build is climate what if, because this is not really, current climate models aren't that great at modeling what ifs. And that's because the climate models are essentially weather models, and the climate is a chaotic system, which I show as these 2 arrows on the right, where small perturbations of their initial conditions diverge. So you have to spend a lot of time getting rid of this initial condition noise. So it's difficult to get good signals on what if. So there are many questions for mitigation, like where should we plant trees? Should we paint city roofs white, or should we plant trees on them and make them green? Should we plant kelp? Should we divert planes to minimize contrails? Things like that. And right now, the climate models can just barely answer these questions with very large error bars. So I'm hoping machine learning can help that. So that's some future work. So I'll wrap up my talk. The 6 lessons that I've learned about applying machine learning and climate change are the following. Climate change is all about accounting, so you have to be careful about how you account for pretty much anything. Every climate change project seems to boil down to accounting. Don't worry about the CO2 produced by your AI or machine learning. Just go ahead and use it and work on climate. Load shifting is a very effective method for reducing your direct carbon footprint. There's a lot of leverage there, and it does seem to work. I advise engineers to optimize. Don't leave your job and run off and do something in pure climate, but stay in your job and be climate aware. The three styles of AI climate applications, to repeat, are sort of autonomous climate-aware decision-making, large-scale sensing of the world, and large-scale modeling of the world. And if you're doing large-scale modeling of the world, I recommend replacing empirical models with machine learning models. So given that, that's the end of my talk, and I'll hand the floor back to Herman.
Hi, Sean. Thanks a lot. So unfortunately, it was not you who was disconnected. Well, fortunately, it was not you who was disconnected. It was me who was disconnected. Not being in the cabin, so I couldn't follow everything you were telling us. Anyway, thanks for your very interesting.
Hope I wasn't disconnected. We'll see.
Well, I was. Okay, thank you for your extremely interesting talk as far as I could follow, but I think I now want to invite people to ask questions. I think I would like to ask Michaela first to ask a question. Michaela, are you ready?
Oh, yes. Thanks, John, for your nice presentation. I was wondering, what's your point of view in terms of what could be the role of politics here? I mean, climate changes are really like a critical issue for the future. We all know it. And for sure, technicians, engineers, scientists can contribute. But what's your point of view in terms of politics? And as engineers and technicians, how can we actually act on that?
Well, policy, I think, is super important. I talk to a lot of startups that really, and they're very sincere people who want to work on climate change. And so they're engineers, for example. And then almost always they run into this terrible dilemma where they could go for they can go for something that's profitable, but much smaller climate impact, or they could try to go for a big climate impact, but then they can't make enough money to sort of justify having a company. And so I think policy is really needed. It doesn't have to be a global carbon tax, but just to make incentives for companies and engineers and people to just work and encourage climate mitigation. It could be done sector by sector. So I think it's very, very important. In fact, if anything, it might be more important than the next AI algorithm or whatever, just to make sure that the incentives are in place. I don't know if I have a good suggestion. The one suggestion I have, if you want to get involved in policy, is to band together, because it's harder when you have individual voices versus if people kind of come together. So, look for organizations. I mentioned workonclimate.org. That might be a good sort of gathering place to find out, although that might be more technically oriented than policy oriented. So I don't know if I don't know of a unified place to talk about policy for engineers, but you could at least try these gathering points like workonclimate.org or climatechange.ai.
Okay, thanks, John. Keshav is next, I think.
Thanks, Herman. John, thank you for your talk. I wanted to take this time to kind of tell you about eEnergy', which is a new initiative from ACM. And so this conference, which precedes eEnergy', is now under the kind of auspices of the SIG. And many of us come from SIGCOM, there's a background of communication, but we also have members in the SIG who come from the building systems community, civil engineering community, who are interested in sort of these aspects. The reason I bring it up is because you mentioned climate change.ai, which is certainly doing some very good work, but with very much an AI focus. What we want to do here is to have other tools besides AI and other approaches, such as optimization, or even traditional power systems engineering, but with the strong focus on carbon footprint reduction, energy efficiency, and moving forward in energy and society and things like that. So I would, part of it is like a sales job to tell you about the SIG. It's a new SIG. It just started a few months ago, so that's part of it. And the other thing is we very much welcome partnership with Google as appropriate. Both as a place for Google engineers to participate and publish papers, to take part in the organization as they do with other SIGs, And to the extent that there's can be something that we could help Google or Google would help us, we would be very eager to talk to you. And so that's just and so I'm the vice chair. Prashant Shenoy is the chair. I don't know if Prashant is on this call, but we are certainly happy and interested in moving forward the agenda that you presented over here, and having a footprint across the world. So as you'll see, the participants here from around the world in multiple time zones. So that's what we bring to the table, and so we very much would like to do that. Thank you.
Thank you, Kishore.
John, do you have I mean, actually, I was about to ask a similar question to you. It would be great if, let's say, we could ally with Google one way or the other, really, because, I mean, we are academics, but we're also very much interested to collaborate with industry. And I think data center is a very important topic anyway in our community. There are many representatives of data centers. So it would really be nice if we could join forces in this respect somehow. If you see a potential for that, would be really good. And
I think there could be, yes. I'm certainly happy to. We could talk about this offline, but I'm happy to introduce you to people like Anna or Ross Konigstein, who are the drivers behind, for example, that space and time shifting thing.
Okay, next question. I think Sebastian is next in the row, or I can see.
Thank you, Herman, and thank you, John, for the very nice keynote. First of all, Keshav is totally right. eEnergy is the place to be, so I have to also push in that direction. But that was not my question. I think Google is setting a very strong example here in taking this aspect seriously and looking at, with the metric that you presented, in optimizing the company's foothold and footprint. But how do you see Google's role also in encouraging, I would say, the end user? I mean, everyone uses Google, and in the end, we as end users will play a huge role in adopting, in changing our consumption behavior and everything else. And we probably are not the norm. We do so, we research this, we have a deep relationship also emotionally to the topic, but I would say most of the people on this planet don't, probably, but they use Google applications and software. And is there a way that you can encourage them? Or are you already doing this, taking this into account, using the position that you uniquely have to also imprint this notion and this aspect stronger in our everyday life?
Well, this is a very interesting topic because it boils down to where are the leverage points. I mean, we're certainly talking about what we can do. We try to be an unbiased presenter of information. In other words, we don't want to, have we want to. Google's here to organize the world's information. That's our mission. So we want to make sure that people have access to the information. So the question is, if they're actively looking for climate information, we'll try to provide that. So that's part of our core mission. Going back to the leverage, I always think about leverage points because climate change is such an enormous problem. Certainly consumer behavior is one leverage point, but at least my belief, I don't know if this is true of Google, is that doing things, we work a lot with partners. I didn't have a chance to put in this talk. For example, my team works with a fusion company called TAE, and we're trying to help them kind of reach fusion break even. I mean, that's going to be a long term. I mean, I think there might be fusion break even soon, but it might be decades before fusion energy will make a 10%, impact on electricity. But the whole point is that there could be leverage. There could be more effective leverage for technologies instead of trying to lever consumer behavior, lever like industrial or engineering behavior. Because again, one engineer, that goes back to my 3,000 ton number. One individual can only control, I don't know, it depends on whether they're a typical, the median person on the planet is probably less than a ton. Us people who fly around might be tens of tons. but engineers themselves and industrial companies, especially companies that produce electricity or that have very large scale industrial processes, they are up in the sort of millions of tons scale. So I think there's always this assumption that, oh yes, consumer behavior is the right way to fight climate change, but I think you might want to question that. Look, in COVID, I don't know about worldwide, and I don't know if the numbers that come, but everyone had this very large disruption in their life in COVID, and that only kind of seemed roughly reduced emissions by about 10%, which is like 1 year worth of what we have to do. So consumer behavior is important, but I think we have to look for the leverage points. And so it sounds cool. I mean, by the definition that I heard from about SIG Energy, it sounds like it's actually very much focused on kind of industrial or manufacturing or power systems, which I think actually is the place of highest leverage. And again, Google wants to help. We want to partner with these people and use our large-scale computation and machine learning for that. So I know that, sorry, it's a very complicated system, so my answer may have been sort of rambling, but that's sort of the picture I'm trying to paint. Did that answer your question approximately?
Yeah, totally. Thank you so much.
Okay, sure.
Okay. Let's move on to a few further questions. Astrid, I think you're next.
Yes, thank you, Herman. Thank you, John, for the nice talk. I very much liked your kind of underlying, notion of stay on your job and do what you can, don't thrive for the large projects, but simply use your expertise in whatever you do. That's quite nice as a message. I have a question regarding your last lesson. I think it was the sixth one on how to use trained models in combination with the physical models that you have. That is, on your slide, it's quite easy. You have the physical models, the empirical models, and then you somehow shift and combine them. But actually, that is not that easy. We are just starting a project in that context where we say, get best of two worlds. So get the trained model and combine them with the empirical models that we have, and somehow combine these as good as we can. But what is your opinion on that? Is this a new methodological area that we should put more emphasis on? Because it's not that easy at all, even if it's kind of trivial, that it would be a good idea.
Oh yeah, no, sorry, I didn't mean to imply that this is easy. Partially because you have to get representative data regardless. I think the lessons that I'm getting for machine learning in general, let me go back outside of sort of physical models. One of the very early successes of machine learning was, you may have heard of the MNIST data set. Essentially, it's the handwriting recognition. And a lot of what was used, maybe I'm going back too far in history, but a lot of people were trying to build in models of how handwriting is formed, or what typical handwriting is, like almost like a physical or a psychological model, and those were terrible, and those did not work at all. When people use convolutional networks to train on MNIST, it has sort of light physics where it says, you should be immune to sort of shifts and perhaps dilations, and so that's sort of what I'm advocating. So instead of a lot of these sort of very granular physics models dated back to the 70s. I mean, I'm again overgeneralizing perhaps, but roughly from that era, where what they did is they did some experiments. Like for example, we have people looking at wildfire, and the wildfire propagation models. Someone actually went and burned a bunch of different material and then measured how quickly the flames sort of went through the material. And so the model itself has many, many little components about how flames propagate and this and that, and they're all individually calibrated. And that totally made sense back in the 70s and 80s when a lot of these papers were published, because that's all you could do, right? But now we have much more computing, and we actually have the internet to gather much more data. So instead of getting, my advice is, instead of getting stuck in trying to build very, very, very detailed models or very, very detailed empirical models, try to lift it where there's some sort of general principles, just like this MNIST thing. I want to be immune to, I know that three rivers come together at this point, or I want to be immune to shifts, as opposed to trying to take an existing empirical model with 100 parameters that might not be differentiable and trying to sort of tune that, which might be very, very difficult. Try to pull the model up to something sort of simpler and having hopefully fewer parameters, or perhaps easier to fit sort of end-to-end parameters. So it's not at all easy, because you have to find the data, you have to build usually a differentiable model, but we found that it's worth it, that essentially these end-to-end models that have less internal structure tend to be better calibrated because they're sort of more general. I don't know if that answered your question.
Yes, thanks.
Okay.
Harvard, do you have a short question?
Yes, thanks again, John, for the very interesting talk. And it's really great to hear how much Google is doing to reduce its carbon footprint. And like you talked about the impact of AI. Now, if we look at the end consumer impact on energy consumption, that's human intelligence, not AI, but HI. And I think, like in some way, following up on Sebastian's question, the challenge, I think, is to get more human users and customers to actually utilize the potential of artificial intelligence. But for that, maybe we need some kind of explainable AI. Yeah, the human has to understand actually what AI is doing for him or for her. And I don't know to what extent Google can contribute to that, to get more people to actually using AI for improving their local footprint, because that's a significant part of the energy consumption. And if we can do something there, it would be great. And you showed these examples of including the flood predictions in Google Maps and so on. And so maybe some things like that can help.
Certainly, there's a number of people at Google who are very much into, well, there's a whole new group called responsible AI, and part of that is explainability. And people are hard at work. We're not there's no monopoly there. We're part of the academic community in terms of explainable AI, in terms of the research team. What I think is you bring up obviously humans are very important. One perhaps less studied part, there is this subfield of computer science, HCI, like ACM Chi is one of, a very large SIG in ACM. And so I wonder actually if the right answer is to figure out sort of the human AI interface. Let me tell you an elegant example, at least I believe it's elegant, which is the Nest thermostat from Google. The humans don't have to know, they work very hard. The humans don't have to know what the algorithms are inside of it, but they have to have a model of what the Nest thermostat wants to do, and that will then save them money and save them energy, if you see what I mean. So it's sort of instead of saying, oh, humans, there must be an interpretable AI for what humans do. That's one, to me, interpretable AI should be a branch of HCI, because fundamentally explainability and interpretability is it's a human defined thing. It's not a mathematical thing. It's a human thing, because the humans are consuming it and they want to be satisfied. But explainability is just one path to having a satisfying HCI, a satisfying experience. And so things like the Nest thermostat, if we can do things that make the humans oh yes, this thermostat, it'll save me energy. I'll give it feedback if I'm too cold or too warm or something. That's kind of a very elegant thing. And there may be other such interfaces that don't require the AI to kind of explain what it's doing, but at some other level, if you see what I mean.
Yeah. Okay. Thank you. But actually, Nest is in particular the Nest. There are nice stories about how humans actually try to convince Nest that certain temperature levels should be there in the rooms, and they try to figure out how they can actually teach Nest to do what they want.
I see. Okay, well, so maybe it's not as as elegant as I thought, but yeah, again, nothing is perfect. I guess we all have to.
Yeah. Thank you.
Mm-hmm.
All right, there are a few more questions, I think, including myself, but I think Sonia would be next, if I checked it correctly.
Thank you. Thanks, Herman. Somehow my hand raising function didn't work. I have a question regarding your conclusion number 3, load shifting works. You were talking about data centers and shifting workload both spatially and temporarily. Do you have any rough assessment as to which percentage of workload in Google data centers is shiftable, A, from geographical point of view, B, from temporal point of view?
I'm afraid I personally don't, because I was not a member of that project. Ross is in my team, but I'm embarrassed to say that I don't actually have that number at hand. So you might have to either ask Anna and Ross, or I think they have an archive paper out just very recently, like in the last week. So you might be able to sort of trace that number down. I'm afraid I don't have that number in my mind. I'm sorry.
Okay, thanks.
Okay, if I may have a follow-up question to Sonia's question. I mean, load shifting in space and time, of course, is pretty obvious. How about the infrastructure itself? I mean, there's the Google network and the Google data center networks, and of course, these are highly complex networks with, let's say, hundreds of thousands of computers, of blades. Is there anything you're doing there? I mean, you as Google, or looking into energy or energy adaptation and things like that?
For networking, not that I know of. Certainly, one thing I didn't talk about was that Anna and Ross had to be very cautious, right? There are these reliability metrics, and the data centers have to stay up, so they have to be very, very careful to not. They want to obviously save CO2, but they have to obey certain reliability principles. So I don't know if changing the networking can be done in a way to keep things very, very reliable. It may be possible, but I certainly don't know. I don't know of any work there.
So things like optical switches is not a hot topic, or
it may be. Again, I'm sorry. It's a little bit outside of my field, so I don't actually know what's going on there. I apologize.
Okay, sorry. Okay, so I think Omid might be next.
Thanks, John, for the keynote. I just had a question related to this notion of end-to-end modeling and also sensing that you mentioned in one of your slides. So are there fundamental limits to passive sensing? Because in a lot of physical systems or cyber-physical systems, we actually do not have overexcited system, right? So the system is underexcited. If you just want to passively sense, you have to do this for many years in order to be able to find some interesting observations that can be built, that can be used, in fact, for end-to-end machine learning and end-to-end modeling. So so if you can comment on that, that would be great. And what are the roles of, let's say, different industrial partners that we have here to let the research community experiment with their systems and try to create some interesting events in order to see what happens?
I think you struck at the heart of a very good and complex issue. You may be thinking of it as from your language, I suspect you might be a control theorist. I think of it, there's a branch of machine learning called causal learning, where you're actually, of course, 98% or something very large fraction of machine learning is statistical modeling, which relies on correlation. But that's not, as we know, is not the same as causation. And there's very strong mathematical results, mostly out of Judea Pearl at UCLA, saying that observation in general, observational data is not enough to learn causal modeling, that you have to stage interventions. You have to poke at the system in order to learn how to do it. And ironically, for a lot of these systems that we want to know about, things like floods, we can't really stage interventions. We can't, like, add more water to a river. So you're right. You've exactly identified a problem that we're still wrestling with. I don't have a great answer other than one thing that people have done in machine learning is to supplement data with artificial data. So this is a common theme where you take data and you add sort of known perturbations, and that expands your data set and expands it beyond sort of the space, maybe the very, very limited space of sort of natural systems. Now it's hard to make a general recipe, or I can't give you an example. Well, I can give you some examples, but I don't know if I can give you a general recipe that will work on all possible problems. For example, back at Microsoft, the Kinect was trained on computer graphics. So essentially what you did is they used real data. Sorry, it's kind of dusty up here. Real data, and then they supplemented it with sort of computer graphics data. This is trying to, like, identify what the pose of the person was. So it's sort of like, are their arms are up or down? And so they added lots of data sort of artificially by using computer graphics. The same thing might apply to some of these physical models, that if you can know if there's some equivariances, this is what I mean by light physics, if there's some equivariances that you know about your system, you can apply them in the data generation process to sort of both expand the data set and to sort of make it to have it the sort of the invariances or the equivariances that you really want, that you know are true. That's sort of what I mean by the light physics. But it's hard to have a general recipe, and I can't claim, there's no mathematical proof that will always work. It just seems to often work. But you're exactly right that in general, to learn causal models, you have to have interventions, and that's, either the things are safety sensitive. Sometimes you can do it, like our fusion work. We actually have a human in the loop. It's kind of fun. I didn't talk about it there. You have physicists in the loop. So you try to optimize the plasma in the fusion, and then you say it's almost like we call it the optometrist algorithm, because it's A or B. Which experiment do you like more? And often they can't assess there's no objective metric that they can verbalize about what makes this plasma better than. I mean, there's stability and there's energy, but there's trade-offs. And so we just ask the physicists, like, which one's better? And they say, well, then this one's better, or that one's better, but it's obviously going to damage the apparatus, so never do that again. So by having kind of optimization with human in the loops, you could try to get at some of these systems, because that is an intervention, right? And so you can build a model you can build an optimization model by asking the human for sort of preferences. And again, that's an example, a positive example, which would be a delicate machine. You're asking about access, but there, at least the optimization is performed in such a way to protect the machine by always going back and asking the human, and not just letting the optimization run off. So I don't know.
Okay, thanks a lot. I think it's now time to leave you off the hook, John. So because you might never come back to us if we torture you too much with questions.
No, it's okay.
Unless there's a very, very urgent and very, very short question, I think I would like to call it a day now and send John back to the mountains. Pleasure. Yeah, and other than that, I would like to thank everybody for the questioning and interesting questions, and also in particular you, John. Great to have you here with us, and very good talk and very nice discussion. Hopefully we'll stay together with Google now in the future, hopefully with yourself also, and let's join forces if you want to. Thank you very much.
Okay. Well, thank you. Bye.
Thank you very much.
Thank you. Thank you for inviting me.
Okay, so I think we can call it a day, right, for our